Hi, in this video I'm going to explain about the Taylor's versus Maclaurin theorem. So firstly we will take a quick look at Taylor's theorem. So let's suppose that x0 is the center of our expansion and there are some interval around x0, which is function of x is assumed to be differentiable, which means by that inside this interval around x0 all higher derivatives of the function do exist. So then here is the statement of Taylor's theorem. So function of x can be expressed in the following fashion. Well, the first part is the truncated Taylor series of the function centered at x0. So we know the coefficients of the Taylor series are given by the nth derivative of the function at x0, which is the center of the expansion, over the n factorial times x minus x0 to the n. But this is a truncated Taylor series, so it begins at 0, but it does not go up to positive infinity, but up to a fixed point, which is n. So this n here is some positive integer, and this is sometimes referred to as the nth degree Taylor polynomial of function centered at x0. As if you express or expand this finite sum out, you will realize that it is simply a polynomial of degree n. So now, of course, the equality is not so simple. There is also an error term. Also sometimes we call them remainder term, which has the following term. So if you see here, the remainder term is the first omitted term of the truncated series after the lowercase n and takes on uppercase n. The next value is uppercase n plus 1. So this is n plus 1 derivative of f at, and we're going to see now not exactly the center of the expansion, but some value close to it times to x minus the center to n plus 1 over n plus 1 factorial. So what Taylor's theorem says is that for any choice of positive integer n, you can make the equality valid if, and we look here, well, we need the value of x to be in the interval where all the higher derivatives of f do exist. So suppose that x is here, then what Taylor's theorem says is that for any choice of positive integer n, the equality is valid for some choice of c of positive integer for some choice of c between x0 and x. So let me call this is c. So we just choose the right value between the center of the expansion and the chosen value of x, and if we evaluate the n plus 1 derivative at this well chosen value c, then the equality is valid. And of course, if we take different values of n, it will take different values of c. So c does depends on n. So you can write like this: C does depend on n. Write C subscribe the uppercase of n to emphasize that the choice of C does depends on the choice of n. But key is that for any choice of n, we can find some values of C between x0 and x, such that if we evaluate the n plus 1 derivative at this point, then the equality is valid. So as we give the shorter name, this, as I have said before, is the remainder, and so we call this is R sub n, as it is depends on the choice of, we call this depends on the choice of positive integer n. Okay, and now the equality is valid for all value of n, and we hope to see the function f(x) will be equal to its Taylor series, not when we start summing at uppercase n, but when we sum all the way up to positive infinity. Then we can simply let uppercase n tend to infinity on both sides of the equality, and let's see what's come out. So, well, as we letting the n tend to infinity, so the truncated Taylor series will become the full Taylor series. So, summing from 0 to infinity, the n derivative of the f(x) at the center of x0, over n factorial times x minus x0 to the n. And we hope is that the function will equal to its Taylor series centered at x0. Well, what about the remainder form? Well, we will think about what needs to happen to the remainder term for the equality between the function and its Taylor series to be valid. So we are saying that both sides are equal for any choice of n, letting n tend to infinity, and function, the truncated series become the full Taylor series, and if the equality to be valid, the remainder term in the limit has to disappear, so it has to shrink to 0. So if in the limit our n does converge to 0, and as we are learning n tends to infinity on both sides, this term will vanish to 0, this term will vanish to 0, and truncated Taylor series become full Taylor series, and f(x) stay f(x), and this is another criteria for a function to equal its Taylor series, and this is Taylor's theorem. A function will be equal to its full Taylor series centered here x0 if the remainder term from the Taylor's theorem does converge to 0 as uppercase N tend to infinity. That's all for Taylor's theorem. So now I will continue to Maclaurin theorem. Okay, for the Maclaurin theorem, it is a special case arises when we take the Taylor series at the point 0. So when we do this, we get the Maclaurin series. The Maclaurin series is the Taylor series at the point 0. So the formula for the Maclaurin series is like this. So we will use this formula in the same way as we do the Taylor series formula. So we find the derivative of the original function and we use those derivatives in our series when it calls for it. The only difference is that we are now strictly using the point 0. So all our derivatives are evaluated at the point 0. So this is for Maclaurin theorem. So that's all for this video. Thank you.